Assalamu alaikum. My name is Abdullah Ajmal and today I will be explaining in detail our semester final project of subject microcontrollers and embedded system. Our project supervisor Sir Umar Farooq and our lab supervisor Sir Umar Raza. So the project assigned to us was a line following robot by the name of Rehber. So this is a proposal. Basically the concept was that we had to create a robot that had to follow a particular black line or white line. It should include voltage sensor and current sensor for battery management and monitoring. It should control an ultrasonic sensor or an IR sensor for the detection of the obstacle in the path of the robot, and the robot should revise its path if it encounters some obstacle in its path. Moreover, we also required a SD card to store the information about the project onto the system, and an LCD screen to show the results of the input voltages, currents, and the path, whether the obstacle has been detected or not onto the LCD screen. And we have to use IR sensor for the line path detection and for the obstacle detection. So this is the proposal. So we proposed a design of line following robot that should cover a given path in the minimum possible time while displaying all the details of its voltage, speed, obstacle, and on the LCD screen, and also save the data onto the SD card module. So we designed an embedded system for a line following robot that follows black line or can be changed for white line when it moves from point A to point B, and also detects T-junction by the help of IR sensor and displays the value regarding voltage and current using current sensor and voltage sensor onto the LCD screen. So basically, the 4 points that we kept in number one were reliable construction, cost effectiveness, and multi-spec robot, and collection of various type of data that we needed to store and display. So first of all, let's move towards the reliable construction. So in reliable construction, we included an on-off button for turning on and off the robot, and implemented the circuit onto breadboard as well as PCB. And we have cost effectiveness, in which we made our robot more cost effective by purchasing parts from a wholesale dealer, and we used minimum number of sensors and other modules required for our data and our project. And the different type of data that we collected through this project was current that was required by the motor, the speed of the motor, the voltage that was being provided to the circuit, and checking for the detection of black line and white line for the robot, and to follow the line. And then we have a system for monitoring batteries and microcontroller and the LCD. Then we have the product comparison for so basically there were three different products on which we performed a comparison. First was IR sensor and IR sensor array, then we had the microcontroller, and then we had the PCB board. For IR sensor, we went with the IR sensor individual module, so because it is more cheap and easily available, and if a sensor blows out or fails, so we can replace that individual sensor according to our desire. But in case of an IR sensor array, it is costly, it is not available everywhere, and it is the sensors are directly attached to the PCB, so they cannot be changed if they are faulty. So if we need to change, we need to replace the whole array. Then we had the microcontroller. We went with the Arduino Mega 2560, based upon the ports availability for input and output. We could also go with two Arduino Uno, but we had to implement serial communication between the two Arduino as master and slave to display data and receive data from one to another. uh, that Mega 2560 was a little bit costly as compared to Arduino Uno, because of its size and the port availability, but we require that port availability for our project, so we went with uh, Arduino at Mega 2560 instead of Arduino Uno. Then we had the decision for choosing our particular type of PCB board that we needed to select. For the selection of PCB board, we went with the fiberglass PCB instead of a normal plastic PCB because in the previous semester project, really we made the same project using plastic PCB board. The errors that and issues that we encountered was that the copper path was destroyed after some time of testing and trial. After soldering and even after drilling, the copper paths were removing from the PCB board, so we needed to replace that. So we went with the fiber board PCB. It is much more reliable and strong, but it is a tad bit costly. So for the improvement of the circuit and more versatile implementation, we went with the fiber board PCB. uh, then we have the team roles and details. Safir performed component buying, writing code, updating the code. Then I myself went with the technical work, assembling hardware and PCB making. Wajahat went with the schematic and simulation and making the circuit on Proteus. So this is the work breakdown structure. First, in phase 1 we did simulation on Proteus. In phase 2 we went out for buying component. The component buying of component was based on different phases. We first went to Rawalpindi to buy most of our component. Then we went to G11 electro store to buy some of the component that were missing and were not available. Then phase 3 was PCB making, and phase 5 was 4 was breadboard implementation. Phase 5 was complete final project testing, and phase 6 was PCB implementation, and phase 7 was report making. So this is a Gantt chart that represents that what were the uh, dates on which the tasks were performed finally, and this was the expected budget. So the component that included one robot chassis, female to female and male to female jumper wires for connection, soldering wires, sticker sheets for the printing of PCB, ultrasonic sensor. Then we had seal header for the connection of Arduino to the PCB that integrated Vero board for the testing of sensors. Then we had current voltage sensor, current sensor ACS 712, double-sided tape for mounting of sensor and other PC board onto the robot chassis. Then we had ferrichloride for the etching of our PCB. IR sensor, we used 5 IR sensor and bought one extra adhesives. We have L298N motor driver, which has built-in H bridge for the direction controlation. Then we had the microcontroller breadboard. 18650 cells were used for the implementation of a built-in power bank, which eliminates the use of external power supply. And we also used a power booster module to increase the voltage so that they can drive motor more powerfully using 12 volts instead of using a secondary battery pack of 12 volts to power the motor driver module. Then we had a little bit of experimentation of different methods of PCB printing by toner transfer heat method and toner transfer acetone method. So basically both of the method have their own pros and cons, so we went with the mix of both acetone method and the heat transfer method of toner. Then the total cost of our project went up to 11,500, including all the sensor that we burnt out in the testing phase. So basically, what is a line follower robot? So basically, a line follower robot is a robot that moves from one fixed position to other fixed position based on the placement of a black or white line onto the floor. The robot follows it and performs various tasks that are added to it. So now let us move towards the move toward the products and their specification. Um, So basically, first of all, we have a microcontroller. Microcontroller is a compact integrated circuit designed to govern a specific operation in an embedded system. Microcontroller includes a processor, memory, input-output ports, single chip. Some of the practical applications of microcontrollers are found in vehicles, robot, office machine, medical devices, mobile radio transceiver, vending machine, and home appliances. So basically, it has the following component: it is a CPU, memory built into it, which is SRAM. Then we have input-output ports for the input receiving and output instructions. Then we have analog to digital converter, digital to analog converter. So basically the controller that we went was Arduino Mega 2560. So this is basic pin out of the Arduino 2560. So it is 60, it has 54 digital input output pins, 16 are analog pins incorporated on the board that makes the device unique and standard from other. 15 are used for PWM, which is pulse width modulation, that can be used to control the output current and even the speed of the motors when connected to it. Then we have a power jack if we use to control the Arduino Mega with some external power source. The board has built-in 5 volts and 3.3 volts voltage regulator, so that different modules can be run according to it by using these built-in modules. This is the pin configuration, the pin names with the respective numbers, which can also be seen online. So now let us move towards the LCD display. For the LCD display we used a 16 cross 2 in the final, but we also use 16 cross 4 LCD display. It is a dot matrix liquid crystal display module specially used for displaying letter, number and symbols. So these are the connection pins. Let me zoom. First of all, we have a ground connection VCC V0. This is for contrast adjustment on the screen to display the data. Then we have write enable and read enable. Then we have total enable for our LCD. Then we have 7 or 8 of our data lines. So we used 4 bit data transfer between our module and our Arduino. So we use 4-bit data communication. They can also go towards the 8-bit data communication mode. Then we had A and K for the LCD's backlit configuration. So this is the table that is included with the report, in which all of the specification of the pins have been described briefly. Then we moved towards the robot chassis. That we used was acrylic and had two gear motors with compatible freely with movable and other accessories. Basically we had rubber wheels and other components that were also included with it, but we did not use the battery box. So the motor that we used were rated for 3 to 6 volts and can also go up to 12 volt for maximum power. The unloaded speed was 120 rpm, loaded current was 190 milliampere, and maximum torque was 800 grams centimeter. These are the dimension and weights. These are the wheel specs. That wheel width is 30 millimeter and diameter is 65 millimeter. Then we use a tachometer. Basically a tachometer that we used was optical tachometer that worked on the basis of a black disc having slits into it, and it counted the number of slits per second, and based on that it gave us the respective speed of our motor. So it was LM393 based sensor, speed measuring module by pulse count based on the interrupt pin IN0. RPM measurement was done on that. It used groove optical coupling sensor whose width was 5 millimeter. It has output straight light, output high level and low output level on it. If covered it would give output high level, otherwise it would give output low level. So basically LM393 is a voltage comparator and determines the voltage difference when detected. So this is the tachometer module that we used in our project for sensing the speed. Then we had a SD card module. So SD card module was connected onto the specific serial communication SPI pins from pin 50 to 53, which included 4 pins for master in, slave out, slave in, master out. Then we have clock and CK pins for the controlling SD card module. So it is was used to store our path information onto the SD card module using SPI protocol, and we used a micro SD card to store all of our information. So after the compilation we can remove the SD card and see which of the things that it has stored onto the it. So it required a power supply of minimum 3.3 volts, so it was Arduino compatible and was used directly. Then we have motor controller module or motor driver. So we used L298 and motor driver module in our robot. It is a high power motor driver module for driving DC motor. It consists of L298 motor driver IC, 78M05 voltage regulator, resistor, capacitor, power LED, 5-volt jumper integrated within a circuit. So we can connect up to 4 DC motors or 4 DC motor with single direction control and 2 DC motor with reverse and forward anti-clockwise and clockwise rotation control. The 7805 volt regulator will be enabled only when the jumper is placed when the power supply is lesser than 12 volt. Then the internal current circuitry will be powered up by the voltage regulator. So this is the L298N module that we used in our robot. So this is the complete circuitry. This is a voltage regulator 7805 that is built in with the L298N. So this is how we connected our motors for testing. So it has a built-in heat sink for better heat dissipation. So this is the pin configuration of our L298N motor driver module. So basically for the power source of our robot, we made a makeshift power bank using 18650 lithium ion cells. We use approximately 18650 cells connected to them in parallel. So we had the final capacity of 40,000 milliamp hours. 40,000 milliamp hours, and because one cell was rated for 6800 milliamps, so when connected in parallel it increases the storage capacity. Then we use this power bank module for powering up a robot. It has a built-in on-off switch which was directly used by our robot for turning it on and off. So it has a charging voltage of 5 millivolts, charging current of 1000 milliamps, and rated USB output voltage of 5 volts with a current of maximum 2.1 amperes. So it was compatible with the lithium ion and nickel cadmium batteries and polymer batteries, but it was not compatible with dry cells. This is the efficiency. Then we have ultrasonic sensor. We use HCSR0404 ultrasonic sensor for our robot. It was connected on the pin 9 and pin 8. Echo and trigger pins were connected. So one of the pin is used to send a sound pulse as output with 10 microsecond delay, and other is for receiving the pulse from the output path so that they can work properly. Obstacle in the so we have used ultrasonic sensor to detect obstacle in the path that we have created. Our robot will stop movement when it detects an obstacle. It is 4-pin module whose pin names are VCC, trigger, echo and ground respectively. This sensor is most popular in measuring distance or sensing objects. So basically it calculates the distance based upon time and receiving the output waves and the distance they travel based on that. So one of the parts sends output to in form of sound waves, and when obstacle is detected, the reflected sound are captured by the receiver, and applying the formula of time into speed of sound, we get the distance between the obstacle and the robot. Then we used IR sensor. The IR sensor that were used were HW201 IR sensor. It has two component, IR transmitter and IR receiver. The transmitter sends ultraviolet radiation towards the output surrounding, and the reflected light is absorbed by the receiver, and it detects whether on which type of reflective surface we have placed our robot or our particular surface that we are working with. So it has basically 3 pins, VCC, ground and out. For 5 volts is operating voltage, and it can be derived from 3.3 volts to 5 volts, and its range is up to 12-20 centimeters. So this is the detailed pictorial representation of our IR sensor. So basically we have IR receiver, IR and IR transmitter. This is the potentiometer that is used for distance adjustment and detection. So one LED shows when the obstacle is detected and other LED is for power. Then we use voltage booster. So for our robot we didn't use an extra battery pack of 12 volts. Instead we used a voltage booster based on the XL6009E1 chip IC. So it provides us 12, it gets input from 4.12 volts and boost it up to 36 volts. We use the built-in potentiometer to restrict it to 11.98 volts, approximately 12 volts for our motor driver module. And this is a DC to DC switching boost converter and drive a load of 4 ampere with excellent line and load regulation. The main component is XL6009 IC. It is available in fixed output voltage of 3.3 volts, 5 volts, 12 volts, and adjustable output version. So this is a detailed diagram. So we have two pins for input, negative and positive, and similarly two output for positive output and negative output for ground. These are the specification of our voltage booster module that we used. Then we have the current sensor. For the current sensor, we used ACS 712 block 3 for sensing of up to 3 amperes of maximum current. The current sensor is used in our robot to check if the proper amount of current is provided to the circuit for the proper working of the robot. We use this sensor because it is easy to interface with our robot and calculate and measure the amount of current applied, and it is fully integrable as it is based on Hall effect. So it has basically three pins, one for VCC, one for ground, and one for output of the signal that we will receive respectively from it. These are the specification. We went with this block. With this as uh, sensitivity of 185 millivolt per ampere. So it gives us a deviation of 185 millivolts if no voltage is detected. So we have to encounter that for in our code. Then we had a voltage sensor. So basically voltage sensor can be created based on the voltage divider principle. So basically we also use the built-in pre-made voltage sensor module. It has two resistors of respective values of 7500 and 3000 3000 ohms, 7500 ohm and 3000 ohms. So basically on the principle of voltage divider we are measuring the voltage that we want to measure across some particular component. So this voltage sensor module allow us to measure up to 25 maximum voltage sensing capacity. So it also has a signal pin for the output that we have to receive and use for the microcontroller. We have VCC and ground for the proper working of this sensor. So the voltage sensor is connected in parallel for the detection of voltage, whereas the current sensor needs to be connected in series for the measurement of current that is passing through it. So now let us move towards the basic block diagram. So basic block diagram, we have ultrasonic sensor encoders for the speed measurement, IR sensor for the black line and white line detection, where we have current sensor and voltage sensor for our robots parametric calculations, and then for output we have LCD, SD card and motors for our output. This is the detailed diagram. So we have connected the battery on V in. For the voltage sensor we have used analog 0 pin. For the current sensor we have used analog 1 pin. For ultrasonic sensor we have used digital pin 28 and 29, one for echo and one for trigger. For IR sensor we have used digital pin 8 to pin 12 for the connection of IR sensor. For the rotary encoder, for the encoders for the measurement of speed, we used the built-in interrupt pin built-in interrupt pin 0 interrupt pin, which is on digital pin 20 for the detection of speed for our board. Then we have our PWM drive modes. We have used pin number 2 up to pin number 9 for this. For LCD we have used pin number 23 to pin number 27, for which include the enable pins as well. And for the SD card module we use specific SPI communication pins from pin number 50 to pin number 53. uh, Now let us move towards the uh, Now let us move towards the simulation and respective cases. So basically our robot had included 5 sensors. So based on that we have to control our motors, and for that we implemented 32 cases of state machines on which the desired output will be taken from our circuit. So this is the respective truth table on the basis of which we are running our uh, robot. So let us move towards the Proteus simulation. So this is the Proteus simulation of our circuit as combined as a whole. So we have our microcontroller unit here, and then we have a tachometer unit for the measurement of speed. Then we have a initial unit for built-in boost converter module placement and voltage and current sensor placement. Then we have our LCD module for replacement of potentiometer and our 16 cross 4 LCD. Then we have our SD card module and its complete pin configuration. Then we have our IR sensor array and its complete placement. Then we have motor driver module and its placement, and respectively our current sensor, voltage sensor, and ultrasonic sensor. So this is a PCB layout of our project, and this is the 3D visualizer view. This is the front side on which we have to place, and these blocks right here are self-made blocks for the boost converter module and current sensor and voltage sensor respectively, so that they can be directly placed onto our circuit. As we can see here, this is the placement for motor driver module, this is the placement for our boost converter, this is the placement for our current sensor, voltage sensor, and placement for our external battery. This is the placement for our IR sensor array, which is based on, this is for our tachometer, this is for our LCD potentiometer for contrast control, and this is for the enable control for our motor. So now let us move towards the simulation of our IR sensor with our motor. So we can also uh, as we can see, all of the sensors are detecting 0. So let us make one of the sensor high, so it is now moving forward. Similarly, if we make this, no, it will move right. So we are moving opposite motor to move in opposite direction, so that the robot can function properly and move according to our curves in the path. Similarly, if we stop this, and now it will move left, and similarly if we make both of them high, so it will stop. So as you can see, as we have made all of them high, so it has stopped. So this is a sorry, our motor driver module, which is accordingly connected to our right enable, left enable, and respectively int 0 to int 4 for our motor connection for positive and negative. And the LCD display shows us that whether the path being followed is correct or not. So now let us move towards the implementation of the voltage module, voltage sensor. So basically there is no pre-built module for our voltage sensor, so we needed to create our own voltage sensor based upon the resistances. So we use the resistances that we used are 3.4k and 10k. So as we can see, it is measuring voltage of 24.9 volts based upon the voltage that we have given here. So that's all for voltage module. Then we have moved towards the current module. So this is the current module. It measures the current that is going through this 12 volt bulb. So as we can see, it is measuring 0.238 amps, and we can see that the amps that we are measuring through our ammeter is 0.21, so it is approximately correct. So similarly we have implemented this stuff over our main circuit, which is here. We have implemented same sensor, but we have included seal headers and connection ports for our PCB, and better placement for our components directly onto our PCB board. So now let us move towards the videos. Now we will move towards the software coding parts of our project. So basically, this is all of our project is coded in Arduino IDE. So basically here we have a block for our initial information for our line follower sensor. So we have connected them from pin number 8 to pin number 12 of our IDE. Then we have a motor enables for our PWM control for right motor and left motor. Then we have then we have included the library for liquid crystal, so through which we are controlling our 16x4 LCD display. So these are the pin configuration. Then we have configuration for our voltage sensor. So basically we have in voltage sensor, the resistances for our voltage driver that we a voltage divider that we have used are 1000, so which is 10 kilo ohm and 3.5 3.4 kilo ohm, and we have set reference voltage of 5. So basically in when using the current sensor, we don't when using the voltage sensor, we do not need any kind of pre-adjustment for the value detection. So it gives directly the value that is detected. So for current sensor, we have included the library for filters, and for sensitivity 185, as we can see that when no current is detected, it gives us a value of 185 volts. So in order to compatible, in order for the compatibility of that sensitivity, we have to use that. And for the offset voltage value, we have used 2.5 millivolts, or we can say 2500 millivolts, or 2.5 volts that we have used. So then we have the library looping.h that is used for our ultrasonic HCSR04 sensor with trigger pin 28 and echo pin 29, and we have defined the maximum distance that it can measure is 400, and we have included variables for duration and for distance. Then we have for the speed measurement, we have tachometer, for which we have made a volatile integer type counter, and previous millis function which measures time. Then for SD card, we have used SPI communications, serial peripheral communication, and sd.h.begin, and we have created a file, my file object, to store the data. Then we have serial.begin 53 to enable the SD card, and then we have begin the serial monitor. So these are the initial values that we are going to display onto our LCD screen. Then we have given the pin mode to all of our in the respective pins for a particular input and output for the motor PWM drives, and for the input from the IR sensor. Then we have initialize the counter pulse function for our tachometer model, so it will count how much time has passed and how much slits have passed through the U type optical sensor. Then we have in our loop, we have our state machine based code on if else statements. We have also called our code for voltage sensor, current sensor, and ultrasonic sensor. These are the 32 cases as they are discussed here in this Excel sheet, according to which we have coded our state machine. Now let us move towards the end, in which we have our forward function, in which both of the motors will go in the forward direction. Then we have stop function in which both will stop, and we have included the specific SD card write function, which will write that which specific task was executed at that particular time. Similarly, we have left and right. So this is the voltage sensor. So for particularly for voltage sensor, we have just taken the input value and divided it by 1024, as it is a we have 10-bit ADC, and multiplied it with reference voltage, which is 5 volts, and displayed the value directly using voltage divider rule onto the LCD screen. And similarly for the current sensor, we have to subtract the offset voltage of 2.5 millivolts and divide it by sensitivity in order to get the accurate current reading. So we have implemented that formula as well. For ultrasonic sensor, we have set a while loop. So if the distance is less than 10 between the obstacle and the robot, only then will it stop, otherwise it will continue moving towards its target. And for the RPM function, it is just counting the distance traveled and number of points that have passed between the U sensor, and based on that it is giving us the value of RPM. Then we have SD card module function, in which we are just opening a text file and then printing the respective terms for forward, reverse, and stop, left or right, or obstacle detected into our respective SD card, so that if we after running our robot we can remove the SD card and plug it into our laptop and see what it has stored while following that particular path. So now let us move towards some of the difficulties that we faced during our creation of this project. So basically the difficulty that we faced was in availability of libraries. Most of the libraries for our included modules like IR sensor module, ultrasonic module, most of the current sensor, voltage sensor and tachometer were not available. So basically we created those on our own. And furthermore we encountered fatal simulation error due to the echo and trigger pin of the ultrasonic sensor module. So we also tackle that for the then in the design challenges for the PCB. We did not have any PCB footprint for our Arduino Mega, so we created that footprint. And similarly we didn't have any footprint for our voltage boost converter module and our current and voltage sensor, so we also custom created those modules in order to implement them onto the PCB.
These were the templates that were used to print our PCB. This is the bottom layer of our PCB, and this is the top layer of our PCB. Then after the etching and soldering of our PCB, these are the final results. So this is the top layer of our PCB after final soldering, and this is the bottom layer of our PCB after final soldering, and this will be placed on the upper side so that we can watch all the information that is being displayed onto the LCD screen.